Hey guys, so today we're going to go ahead and talk about stoichiometry and using gas laws in order to solve some problems with chemical reactions. To start out with, we're going to start with this problem. A piece of sodium is placed in a 3.75 liter sealed rigid container. The air is removed and replaced with pure oxygen at a pressure of 3.25 atm and 25 degrees Celsius. The sodium slowly reacts with all the oxygen, producing solid sodium oxide. How many grams of sodium oxide are produced? So as we look at these problems, we need to go ahead and ask ourselves, what is it asking for? We clearly see that it's asking for grams of sodium oxide being produced by a chemical reaction. When we do this, we use stoichiometry to predict products and predict reactants. So the first thing I'm going to want to do is go ahead and come up with a chemical equation for this. So reading the problem, I know that I have, I have sodium, and I'm going to go have sodium with just solid, and it reacts with oxygen gas, producing, again, sodium oxide, 2O, which is, of course, a solid. Now I left those lines to remind myself to leave space to go ahead and go back in balance. I see that and I picked Na2O because for every two NAs you need one O. See that I have two oxygens here, so I need to have two oxygens on this side. I do that. Now I have two oxygens, but I have four sodiums. So to get four NAs or sodiums, I do that. And remember that this equation means that for every four sodium molecules, I need one oxygen molecule, and it will produce two sodium oxides. Or we can say, when we're talking about moles, which is just a counting number, we say 4 sodiums for every 1 oxygen make 2 moles of sodium oxide. Okay, so in these, we want to go ahead and find sodium oxide. So I want to know the grams of this. Okay, to do that with stoichiometry, the good thing about these equations, once we have this, we just need to know one of these other things, and we can find anything about any of this equation. So we go ahead and we're going to look into the problem and see what it already gives us. So we see that it gives us a volume of 3.75 liters. It also informs us that there is a pressure of 3.25 atm or atmospheres, and it has a temperature of 25 degrees Celsius. Now that I know that I'm doing gas chemistry right now, I'm going to go ahead and just convert this to Kelvin because we always want our numbers in Kelvin. I'm just going to do it right now. So I'm just going to go add 273.15, and I get 298.15 degrees Kelvin. Okay, so I see that I have a pressure, a volume, and a temperature. So this also tells me that, hey, I have everything I need except for, say, the number of moles of something in order to go ahead and use the ideal gas equation. Of course, we always have R, which is given to you in the ideal gas constant at ATMs is 0.08206 liters ATM per moles degrees Kelvin. And that's just a constant we use in the ideal gas equation. So I can see that I need my mole N, which would be the moles of oxygen, which would be moles of O2. If I find moles of O2, the balanced chemical equation, I can plug into the equation and say how many moles of O2 produce how many moles of this, and once I have the moles of sodium oxide, I can find the grams using the molar mass. So first step, we're going to go ahead and we're going to solve for moles of oxygen using the ideal gas equation. So with these, we always go ahead and we're going to set up the ideal gas equation. We're going to do PV equals nRT, PivNert, and then I'm going to go ahead and solve this equation. Before I plug in numbers, I'm going to solve it for the thing I'm trying to find, which is N, or number of moles. So I want to solve for this. That means I need to get it by itself on one side of the equal sign. So I'm going to go ahead and divide this side by RT, and since I did it to one side of the equation, I have to do the exact same thing. And this results in R and R divided by R is 1 or cancels out. T divided by T is 1, cancels out, and I end up with N equals PV divided by RT. Now I have it rearranged. I'm going to go ahead and I'm going to plug in my numbers. So when I do that, I get, let's see, go ahead and plug these in. We have pressure is 3.25 atm. Volume is 3.75 liters. And this is, of course, divided by R, which is 0.08206 liters atm divided by moles degrees Kelvin. And lastly, I need to find T, which is up here. I already got it into the Kelvin, so I'm going to go ahead and put it in as 298.15 degrees Kelvin. I have all my numbers set up right. To solve, before I do that, I'm going to go ahead and just see what units cancel out to find out what my answer is going to be left in. So ATMs divided by ATMs cancels, liters divided by liters, and Kelvin divided by Kelvin. I end up with moles as my final unit for when I find this. So I'm going to end with moles, and of course this is O2, which is what we want in order to do this stoichiometry. So when I go ahead and plug it in, I do 3.25 times 3.75 divided by 0.08206 divided by 298.15, and I end up getting a number 0.498. So this goes ahead and equals 0.49813666428, or if we just use sig figs, we're going to have about 3 significant figures, the most that we have for any significant digits, and I end up with that 0.498. Okay, so now we have N, or we have the number of moles of O2 for this reaction. So I know that if I put 0.498 moles of oxygen, I need to find out how many moles of this I get, and then I'm going to get grams of that afterwards, of sodium oxide produced. So I'm going to go ahead and start plugging it in. So we start with 0.498 moles of O2 over 1. First step, I want to write the number I want to use for stoichiometry as a fraction as we go along these problems. Now I want to go ahead and figure out, I'm going from moles of this, because again my chemical equation tells me that for every 4 moles of sodium I use, I will need 1 mole of oxygen, and I will produce 2 moles of sodium oxide. I know that I have this, so that also means if we take out this, of course, we have, for every 1 mole of this, we make 2 moles of this. Now this number is smaller than 1 mole of O2. That means that this number is definitely going to be less than 1 mole if we were to solve that out immediately. Go ahead and do the next step. So I'm going from moles of O2 into moles of sodium dioxide, and I'm going to go ahead and make sure that that goes on top then, and I cancel out moles. So every 1 mole of O2 as a ratio, it makes 2 moles of Na2O. Okay, now after that we are in moles of sodium dioxide, so we still need to get to grams, which of course is what the problem is asking for. So we're going to go ahead and to do that, I need to go from moles of Na2O, or sodium dioxide, into grams. So I need to know how many grams of sodium dioxide go into a mole of sodium dioxide. What is that ratio? So to do that, I'm going to go ahead and erase this top part so that I can find my molar mass. Of course, the periodic table helps us find this. Molar mass of Na2O. And we're going to go ahead and say that I know the molar mass, if I find for 1 mole, that means that it's going to be equal to 2 times the molar mass of sodium plus 1 times the molar mass of oxygen. If I look at my periodic table, I can find those numbers, and this is going to go ahead and equal 2 times 22.99 plus 1 times 16.00. And of course that ends up being, let's see here, it ends up being 61.98 grams per mole. And this number, of course, means that for every 61.98 grams of oxygen that I will have 1 mole of oxygen. And the mole tells us how many oxygens we have. So I'm going to go ahead and plug that in. For every 61.98 grams of oxygen I have 1 mole. So now our answer is in grams of this. Moles Na2 divided by moles Na2, cancel our units. Now we can just go ahead and solve this answer. And we get, go ahead and plug it in, we have 0.498 times 2 times 61.98, of course divide by 1, divide by 1, divide by 1, and we go ahead and we get 61.73208. And sig figs is only 3 of them, so we're going to go ahead and 61.7 grams of sodium oxide. Okay, so that is going from starting with a gas and going ahead and finding the grams of a solid. Okay, the next problem that we're going to do, let's go ahead and erase this. I'll leave the gas constant because, of course, we're probably going to deal with that again. All right, our next problem is situated. It says, hey, make sure that's over there. Put my notes together. Says, go ahead and says at a 3.89 gram sample of calcium carbonate, CaCO3 is the formula for it, is placed into a 2.50 liter container and all the air is removed. The container is heated to 875 degrees Celsius and the calcium carbonate decomposes into calcium oxide and carbon dioxide. So we want to go ahead and figure out what is the pressure inside the container. So of course in this problem we're going to be doing exactly the opposite of what we did before, because we have, well, we start with what we know. We have 3.89 grams of calcium carbonate. I also know that after the reaction happens, I'm going to have a temperature. Oh, I'm going to have a volume first. Looks like I have a volume of my container that's happening is 2.50 liters. I also know that the temperature is equal to 875 degrees Celsius, or plus 273.15 is 1148.15 degrees Kelvin. Go ahead and I just convert it right away because I know that I'm going to have to at some point. I also have that I don't have anything else. I also need to solve, if I wanted to use the ideal gas equation, I would also need number of moles, or I would need the pressure. So based on what we have, again, we have we have a chemical reaction happening. So if I have one thing, if I have the mass or the number of moles of one thing, I can predict the mass or the amount of moles or whatever I need for all the other things in this reaction. So let's go ahead and write out the chemical formula and go ahead and solve for moles of our gas that we get. So we see that calcium carbonate, CaCO3 solid, is going to place in this container. There's nothing else in it. And this decomposes into two different things. It decomposes into calcium oxide, which is CaO, which is a solid, plus carbon dioxide, or CO2 gas. Now, the only one of these two things accounting for any pressure is going to be just the gas. If both of these are a gas, we might want to add them. We want to find the moles of them before we calculate what the pressure is. But for this case, the solid is not going to be adding pressure to the size of the container, because of course pressure is caused by gas molecules hitting the sides of their container. So I need to go ahead and find out how much gas can cause pressure so that I can use these other things, the volume of the container, the temperature, the gas constant, to find the actual pressure of the container. So real quick, we're going to make sure this is balanced. I have 1 Ca, 1 Ca, I have 1 C, 1 C, I have 3 oxygens and 1, 2, 3 oxygens. So this is already balanced, just 1 to 1 to 1. Okay, we start with what we know. We start with this and write it as a fraction, 3.89 grams of calcium carbonate, CO3, over 1, write it as a fraction. And we're going to go ahead and we know that we have grams. So before I can use this equation, because remember it's using numbers to say for every 1 calcium carbonate, it decomposes into 1 calcium oxide and 1 carbon dioxide. So I need to have this into a numbers or moles. So I need to go ahead and get calcium carbonate into moles first. To do that, again, I need the molar mass of this thing. So we're going to go ahead and calculate that. Molar mass of CaCO3. Okay, to do that, again, we just have to add up the molar masses of all the things involved for 1 mole of that thing. I want to find out how many grams if I had 1 mole of calcium, 1 mole of carbon, and of course 3 of these guys. How many would 1 mole of calcium carbonate make? So I'm going to have, this is equal to 1 times the molar mass of calcium plus 1 times the molar mass of carbon plus 3 times the molar mass of oxygen, because there's a 3, of course. I go ahead and plug that in, and I see that I got 1. And I find in my periodic table that it is 40.08. Let's get rid of the 1. It's the same thing. Plus 12.01 plus 3 times molar mass of oxygen is 16.00. And that ends up being 100.09 grams per mole of CaCO3. Or, for every 100.09 grams, I have 1 mole of calcium carbonate. Or if I wanted to say, hey, I need 1 mole of calcium carbonate, I would need to measure out 100.09 grams of calcium carbonate. So for every 100.09 grams, I have 1 mole. Go ahead and plug that in, and I say I'm trying to get to moles. I'm trying to get rid of grams. I'm going from grams to moles, so moles is going to be on the top. For every 1 mole of calcium carbonate, I need 100.09 grams of calcium carbonate. So now we have the moles of calcium carbonate that we plug into the reaction, and we want to find out how much carbon dioxide, how many moles of carbon dioxide it makes. So that is our next step. We want to find for every 1 of these, we get 1 of these. So we're going to say that there is 1 mole of calcium carbonate. For every 1 mole of that, we get out 1 mole of carbon dioxide. Pretty simple. And then we can go ahead and solve for moles of carbon dioxide so that we can use our gas law to find the pressure in this container after the reaction completes. So, real quickly, I'm going to go ahead and solve my units. Grams CaCO3, grams CaCO3, moles of calcium carbonate divided by moles of calcium carbonate, and I end up with moles of CO2, which is good because of what I want. Plugging this in, I get 3.89 divided by 100.09 times 1 divided by 1. And I end up with 1.45660. Oh, whoops, I looked at a later number. Okay, so I end up with 0.038865021 moles. Or, let's go ahead and use significant digits to round. I mean, you could carry this number through and then do significant digits, but I'm going to go ahead and just cut this off and round it to 0.0389 moles of CO2. Now we're not done, of course, because the question is not asking for just the moles of carbon dioxide. That gives us the moles of the gas in the container, but I want to know the pressure. So now, after using stoichiometry to predict how much of a gas was made, I can use the other conditions to figure out the pressure, which we're going to go ahead and do. So, go ahead and erase some of this, and let's start using this. Again, when we start with the ideal gas law, which we know is PV equals nRT. Now I want to use this, so I'm going to go ahead and start plugging these numbers in. But first, I need to rearrange it, of course, for what I know. I now know N is 0.0 0.0389 moles of our gas. So I have N, I have R, I have T, I have V, so I need to solve for P, which means I need it by itself, so divide each side by V. That cancels, and I end up with being P, or pressure, equals number of moles times R, the constant, times T, divided by volume. And then I go ahead and plug these in to solve. I'm going to go ahead and move, no, we'll just keep it here. Okay, so pressure equals N, number of moles, 0.0389 moles, times R, 0.08206 liters ATM, divided by moles degrees Kelvin, times temperature, which I had already converted earlier, 1148.15 degrees Kelvin. Sorry, that's a little hard to read. Divided by, of course, I still have V here, divided by the volume, which was 2.50 liters. Okay, now it's simply just doing 0.0389 times 0.08206 times 1148.15 divided by 2.50 liters. And I end up with, let's go ahead and move this. This goes ahead, and it equals, we get 1.4560656, or if I round to significant figures, which we have 3 of them, we have 1.46, and we need to figure out the units. So moles divided by moles, let's see, liters divided by liters, Kelvin divided by degrees Kelvin, and I'm left with just ATM, so this is 1.46 ATM. So the pressure in the container, of course, is 1.46 ATM. All right, we're going to do one more problem, which I'm going to have you try to do on your own at first, and then we will check our answer with that. So for this last problem, we're going to go ahead, reset, go ahead and read it. While I erase, we have about 0.044 grams of gasoline is injected into a car's piston, where it burns, of course, and it turns into CO2 and steam. And steam, of course, is just water in its gaseous form. We want to know, once it burns, the temperature the temperature rises, of course, as a result of this, and what is the pressure inside that cylinder immediately after this happens. So what is the pressure right after these gases are produced by this oxidation reaction? So I want you to go ahead and pause the video and try to solve this if you think you can. Alright, hopefully we made it somewhere. Now this is a really tricky problem, and you want to at least come back and show your work. It is a tricky problem because of the multiple gases that are involved in this in the reaction. So first of all, we're going to use stoichiometry. Of course, we're predicting products and reactants in order to solve something about this gas, find out more information about this system. So I need to write a balanced chemical equation. I start with gasoline, C8H18, and that is as a liquid, which will be heated to a gas and then burned. And I add, of course, in the combustion reaction, I have to use oxygen, gaseous oxygen, and go ahead and it produces, again, CO2, which is a gas, and steam, which is H2O, which is also a gas. So, one more chance right here might be to say, hey, I know that I have to now solve for both of these gases because I need to add the total. If I want to find the moles of gas to find the pressure, I need to add the moles of CO2 that this produces plus the moles of steam that this thing produces to find the total moles of gas in the system, which will help me find the pressure. So if that was what was tripping you up, or if you didn't do that, go ahead and pause and try to solve it again. Okay, I'm going to continue on. The next step I want to do, of course, is solving and balancing the chemical equation. I see that I have 18 of these, 18 hydrogens. So over here I see I have 2, so I would do it times 9. When I saw that I did that, it would set off with an offset number of these, so I'm just going to balance. I'm going to double that up If you need more practice balancing equations, of course, I'm assuming that we know how to do that. So we're just going to move with this. Let's see. So we have 18 of those, and that produces 18, which means I need to double this number. I have 16. I just mean 16 carbon dioxides, which means 16 times 2 is 32, plus 18 more oxygens is 32, plus 18 is 50, or 25 O2s. And again, this chemical equation tells us that for every 2 moles of gasoline, I need 25 moles of oxygen, and that will burn up to make 16 moles of carbon dioxide and 18 moles of water or steam, gas. Okay, so then we just want to go ahead and we got 2 separate stoichiometry problems because I want to solve for the moles of this and for the moles of this, and then we're going to add those together to solve. So I start out with what it gives me, 0.044 grams of CH18 or gasoline. First step, I need to get this over 1, right, as a fraction. I need to get this into moles of gasoline. So I need to do the molar mass calculation for this. So molar mass of gasoline, or C8H18. I'm going to go ahead and say equals 8 times molar mass of carbon plus 18 times the molar mass of hydrogen, and that's going to be 8 times 12.01 plus 18 times 1.008, and I plug it into my calculator and go ahead and find out that the molar mass of this is 104.224 grams per mole of gasoline, CH818. That means that for every 104.224 grams, I will have 1 mole of gasoline. So I go ahead and use this because in order to use the chemical equation, I have to have things in moles. This is a number thing. I can't use grams to go across the grams of new thing immediately. I have to have it in numbers. So I go ahead and solve, and I'm going to run through this pretty quickly. This is kind of a checking problem, and hopefully we are about there. So I have grams. I have for every 104.224 grams of CH18, I would get 1 mole of gasoline. 18. Okay. So now I have moles of gasoline, so I can use this chemical equation to say for every 2 moles of this, I make 16 moles of carbon dioxide. So for every 2 moles of gasoline, I make 16 moles of carbon dioxide. Okay, and now I have moles of carbon dioxide. So this is moles of one of the gases we need to solve this problem. And I plug this in, I do 0.044 divided by 104.224 times 16 divided by 2, and I go ahead and I end up getting 0.00338 moles of carbon dioxide. Now you could have done water first, that's fine. Just go ahead and check once we have them both together. So again, to find water, I have to do this process again. So I know I again started with gasoline. I have 0.044 grams of C8H18 over 1, right, as a fraction. And then for my second fraction, I want to plug in my first conversion, or again, I need to get into moles. So 104.224 grams C8H18 for every 1 mole of C8H18. Handwriting's getting a little sloppy. And now, instead of going to carbon dioxide, I want to know how many moles of water I produce in this reaction. So instead, for every 2 moles, again, of gasoline, that I use up, I'm going to produce 18 moles of water. Okay, so now we go ahead and we again solve. We do 0.044 divided by 104.224 times 18 divided by 2, and I end up with 0.00380 moles of H2O. So now I have my moles of this gas and my moles of this gas. So I'm using the ideal gas law. I want to figure out what is the pressure, but I need to know the moles of my total gas. So I do that by adding these together. So I'm just going to add these two, and we end up getting 0.00718 moles, and that is the amount of gas, that is N, or I'll put N over here. N equals this, or which is the number of moles of gas in the cylinder. Okay, so now we need to use that number to go ahead and find the pressure. Free up a little bit of space. This is good because now I have everything that I need. I have my volume is equal to 0.015 liters. I have my temperature is equal to 865 degrees Celsius. Add 273.15 to get it to Kelvin, of course, which ends up being 1138.15 degrees Kelvin. And I have R, of course, and I have now the number of moles of gas in the cylinder, which is the number of moles of carbon dioxide plus the number of moles of water, which is 0.00718 moles. Okay, and we, of course, are trying to find the pressure. Okay, free up a little more space here. I wanted the chemical equation. So, and then I go ahead and start with the ideal gas law again. I say PV equals nRT. I need to solve it for pressure. Divide by V, divided by V. This cancels. I end up with P equals, pressure equals number of moles times RT divided by V. Now I just plug it in and solve. Do some algebra. Let's see, 0.00718 moles times R, 0.08206 liters ATM divided by moles degrees Kelvin times the temperature, 1138.15 degrees Kelvin. Sorry if it's getting a little small there. Divided by the volume, 0.015 liters. I solve this out and I end up with 44.7058. We'll round it off into three significant figures of 44.7 ATM. So initially, right after this happens, these two gases combine to make a pressure of 44.7 atmospheres in the cylinder. And that's about it. Thanks for watching.